concludes. Okay. So now we prove an important theorem. Let H be a Hilbert space. Let K contained in H be a closed and convex set. Then for every x in H, there exists a unique pkx in K such that norm of x minus pk of x is less than is equal to the minimum over y in K norm of x minus 1. So it is the closest point or proximinial point, as I already mentioned in an earlier occasion, and therefore you can find a unique this thing. Further, if H is a real Hilbert space, then pkx in K is characterized by the following relations. Okay, what is the relation? So x minus pkx, y minus pkx is less than or equal to 0 for every y in K. So whatever may be y in K, this inner product should always be negative, and there will be only one point which satisfies this. Okay. So proof. So H is uniformly convex implies there exists proximinial point. That means there exists and in fact there is existence and unique of the proximinial point. Okay, so that we have already shown this. So we only have to show that the characterization is there. Okay, so let y belong to K. Okay, so then let 0 less than theta t less than 1. Okay, and you set z equals 1 minus t times pkx plus ty. So we have pkx, which is the closest point, and we want to show that it satisfies this particular inequality. So then norm of x minus pkx, now this belongs to K because this is in K, y is also in K, and therefore any convex combination will be in K. K is convex, so K is convex. So x minus pkx is less than or equal to norm of x minus z. And what is x minus z? That's equal to, so norm of x minus pkx okay, and then minus t times y minus pkx. So now let us square this and develop it. So you have that norm of x minus pkx square. So I am going to develop this here. So norm of x minus pkx square minus 2t times x minus pkx, y minus pkx, plus norm of y minus pkx square into t square. Okay, so these two get cancelled, so you get x minus pkx, y minus pkx is less or equal to t by 2 times norm y minus pkx square. So now you let t tend to 0, you will get x minus pkx, y minus pkx less than or equal to 0. So that proves one part. So now conversely, so let pkx in k satisfy x minus pkx, y minus pkx less than or equal to 0 for all y in k. So that is the condition you have you have here. Okay, so we are going to assume that condition and show that x minus pkx is in fact the minimum. Okay, so let y belong to k. So you have norm of x minus pkx square is equal to norm of x minus y plus y minus pkx square. So that's equal to norm of x minus y square plus 2 times x minus y, y minus pkx plus norm of y minus pkx square. Okay, so I am going to take the middle term, so I am going to take x minus y square plus 2 times x minus pkx, y minus pkx. Okay, so then I have pkx minus y. Okay, so I have to add pkx minus y, which is the negative of y minus pkx. So 2 times that will give you minus 2 times norm y minus pkx square. There is a plus 1 already, so this will be minus y pkx square. So now this is given to be less than or equal to 0. This is anyway less than or equal to 0, and therefore this is less than or equal to norm of x minus y square. This is true for all y in k, and therefore pkx is the closest point. Okay, so remark, complex case. So replace x minus pkx, y minus pkx by its real part. Okay, and you can try to prove it yourself. Okay. So in general, x going to pkx is not a linear map, it is the projection. Okay, so what are you doing? For instance, if you had a line in the plane, then if you have this, the closed convex set, I have already seen. So what is the thing? It is nothing but the foot of the perpendicular, so this will be the point pkx. Okay, so this is what we have. Now what does this condition tell you? X minus pkx, y minus pkx. So you have a convex set here. So you have pkx, let us say, is the closest point to x. Okay, so x minus pkx, y minus pkx, so are these vectors, and it tells you that this angle should always be obtuse. Okay, so the geometric condition is that this angle in the plane, if you had in the plane, it is saying the closest point from a closed convex set to x in the L2 norm, in the 2 norm, would be this unique point such that the angle between these two vectors x, joining pkx to x and pkx to any element of k should be an obtuse angle, okay, or a right angle, but then it will be always less than or equal to 0. Okay, so that is it. So now proposition. This pk still has some good properties. So H Hilbert, K contained in H closed convex, okay, and pk from H to K is the projection, that is x minus pkx equals minimum y in k norm of x minus 1. Okay, then for all xy in H, you have norm of pkx minus pky is less than or equal to norm of x minus 1. So it's a non-expansive mapping. Okay, so this is a non-linear map in general, and it is a non-expansive mapping. Okay, so proof. So we are going to assume, so what do you know? X minus pkx, y minus pkx is less than or equal to 0 for any y. So I am going to take here an element pky which is a member of k. Okay, so this is true. Similarly, you have y minus pky, pkx minus pky is also less than or equal to 0. So let us rewrite the second one so that I have the same element here. So I have pkx, pky minus pkx less than or equal to 0. So I have multiplied the second term by minus, so I will multiply the first one also by minus so that it won't change. So this will become pky minus y. So now let us add these two. Okay, so if you add this, you have x minus y, pky minus pkx plus pky minus pkx, pky minus pkx. So norm of pky minus pkx whole square is less than or equal to 0. So norm of pky minus pk of x whole square is less than or equal to, you have y minus x pky minus pkx, because I take it to the other side. And now by the Cauchy-Schwarz is less than norm y minus x norm pky minus pkx. So I can cancel one pky minus pkx, so that will give you a norm of pky minus pkx is less than or equal to norm of y minus x, and that proves this proposition. Okay, corollary. So let M contained in H a closed subspace. So it's a closed subspace, so it's automatically convex. Okay, so closed is a particular case. Then PM is a linear map characterized by PMX y equals xy for all y in M. Okay. So proof. So if Pmxy is equal to xy, then obviously x minus Pmx, y minus Pmx. Okay, so we have x minus Pmx with any y is 0, so this belongs to M, and therefore this is equal to 0. Okay, and therefore it's trivially less than or equal to 0. So that way you have this. On the other hand, if you have conversely, let y belong to M. Okay, so then we have to show that Pm satisfies this particular thing. So let me, what do we have? We have x minus Pmx, z minus Pmx is less than or equal to 0 for all z in M. This is given to us. So let me take z, it's now a subspace, so I can take it as, if you take any y in M, you take z equals y plus Pmx, and this still belongs to M. So I can substitute here, so I get x minus Pmx, y is less than or equal to 0. But then minus y is also in M, so you have x minus Pmx minus y is less than or equal to 0. So this implies that x minus Pmx y equal to 0, and that is exactly this particular condition. And that tells you immediately, once you have Pm is defined in this way, it is linear. Okay, so you can easily check from this that Pm is a linear map. Okay, so if X belongs to H and M is a closed subspace, what do you know about X minus Pmx? Its inner product with Y is 0 for all Y in M. Okay, that means X minus Pmx is orthogonal, this is orthogonal to Y for all Y in M. That means the inner product is 0. That's what we mean by saying X and Y are orthogonal. Okay, so this is called, Pm is called orthogonal projection. Onto M. Okay, so theorem H Hilbert, M contained in H closed subspace. Okay. Then M is complemented in H. Recall what is that? Not every closed subspace can be complemented, that is what we saw, and here we are proving that in a Hilbert space every closed subset is complemented. Okay, okay. Proof. Define M_perp to be the set of all Y in H such that xy is 0 for all x in M. Okay, so this is called orthogonal complement. Okay, so this is clearly a subspace because if you have, it is linear in Y and therefore automatically, so M_perp is a subspace. It's also closed. So if Yn converges to Y and Yn in M_perp, then for every x in M you have xyn equal to 0, and that implies that xy is 0, which implies that Y is in M_perp. So M_perp is a closed subspace. What about M intersection M_perp? So if x belongs to this, then you have xx equal to 0, which implies norm x square equal to 0, that is x equal to 0. So M intersection M perp is singleton 0. Then we saw that x minus Pm of x belongs to M perp, we know all this, and therefore H is equal to M direct sum M perp. So every closed subspace is complemented by its orthogonal complement, and therefore this proof is complete. So I have already defined a perp, which is the annihilator. We will see actually that every continuous linear functional in H occurs as an inner product only, and therefore this M perp, the orthogonal complement which I defined, is in fact nothing but the annihilator of M. So the two notations are not in conflict with each other. So our next task is to look at the dual of a Hilbert space and show that every continuous linear functional in fact occurs like Fy is of the form Fy of x equals xy. So this is what we will have to show in the next. Okay.